anywhere from 10 million to 10 trillion degrees Kelvin. In scientific notation, it's 10 to the 7th to 10 to the 13th degrees Kelvin. Okay, really, really hot. And that's basically what the temperature was in the universe from 1 second to 1,000 seconds after the Big Bang. And in fact, at 180 seconds after the Big Bang is a period called nucleosynthesis, and this was the first time that the universe was cool enough to actually form nuclei themselves, like protons and neutrons. Before that, it was just too hot; they would fly apart. We didn't even have that kind of elementary structure. So the standard model of physics is essentially the limit of what we experimentally know as physicists, and it's the study of these subatomic particles. Basically, the idea is that there's 4 forces and 2 types of matter, and each of these is associated with a certain type of particle. Okay, so the 4 forces are electricity, magnetism, the weak force, the strong force, and gravitation. Electricity and magnetism is actually a unified thing. It's electricity on the one hand, you know what electricity is, and magnetism, like magnets, but it's unified. It was unified by Maxwell in the 1800s.
That comes later. Gravity is needs super strength for that.
So the particle that transmits the electromagnetic force is the photon. If 2 electrons repel each other, it's because they're sending a photon between each other that sends them apart. The photon is the particle associated with light. It gives us the electromagnetic spectrum, which includes visible light that we see, but also everything from UVs, microwaves, cosmic waves, X-rays, gamma rays, all these things. Then we have the weak force. The weak force is associated with radioactive decay and things like uranium and stuff like that. It's transmitted by particles called the W plus and minus and Z gauge bosons. Okay. The strong force is involved in holding the nuclei together. It basically glues the protons together, even though they electromagnetically repulse each other, and also sticks them to the neutrons. And the interesting thing about the strong force is that, unlike the other forces, it actually gets stronger at large distances. So, like if you take 2 magnets, the repulsion gets stronger as you push them closer together, right? But with the strong force, the more you pull these particles apart, the stronger the force gets. It wants to pull them all in. It's too short range to do galaxies. And the transmitting particle is called the gluon because, you know, they thought it was really strong, so it's glued together. And then the 4th one, of course, is gravity. And the reason that I save it for last is because the graviton, the transmitting particle, actually has not been seen yet. And gravity has been the hardest thing to unify with the other 3 forces, as we'll discuss.
We're actually trying to save questions.
We have a lot to say, so we're going to try and save questions and then do Q&A at the end. Yeah, otherwise we won't get through. Okay.
Unless it's really quick, like something you just didn't hear right or whatever.
Yes, graviton is part. Okay. And then, so then there's 2 types of matter. There's leptons, which comes from the Greek word light, and hadrons, which comes from the Greek word for heavy. So light and heavy particles. The leptons are the electrons, and then also muons, taus, and neutrinos. The hadrons, on the other hand, are the heavy particles, and they're made up of quarks. Okay? There's 6 different flavors of quarks: up, down, strange charm, and top and bottom. Also sometimes known as truth and beauty. And then each quark also has 3 colors: red, green, and blue. And so these quarks are what are involved in making up a familiar structure like proton, neutron, stuff like that. So at 50 microseconds after the Big Bang, the universe was 2 trillion degrees Kelvin. And this is a phase called quantum chromodynamic phase transition. And basically, this is the first time that protons and neutrons themselves were able to form. Before that, the quarks were just so high energy that they would all fly off of each other. Each particle also has an antiparticle, and Jeff is going to talk about that a little bit. I want to say one more thing, and that's basically, I mentioned that, you know, physicists have been looking for deeper and deeper structure, you know. We've gone from basically 92 naturally occurring chemical elements to now 61 or 62 of these elementary subatomic particles. So it's been a little bit of progress, but we are still looking for something much more unifying. by the way, the reason I say 61 or 62 is because the 62nd has not been seen yet, but hopefully will be seen in this new particle accelerator opening next year.